should see my screen now, and in particular my website. So, good afternoon. Everything is okay, fine. Are you great? And you should be able to see also the video downloadable in my YouTube channel or in Virtuale, video of last week, of course. And if you have any question, please don't hesitate to ask anytime. Okay, good. So let's continue. And as I mentioned to you, we are discussing our introduction. So let's put it in full screen and let's go to the slide where we stopped last time we were here. Okay, so once again, these are numbers about climate change, and try to remember at least the order of magnitude because it helps to get an idea, first of all, of the concept. For instance, it's extremely important that you know that the global temperature is increased of about 1.3, 1.4 degrees, not 10 degrees. So the order of magnitude, if you want to be prepared over a topic, is extremely important. And so you are trying to get prepared on climate change. It's important to know what is the average temperature of Earth. Do you have any guess? What is the average? Global average temperature over Earth. We will discuss it, but I guess that you don't have an idea. It's important to know at least some basic ideas, like it's around 5, around 10, below 0, maybe below 0, because there are several areas over the globe that are frozen, so maybe below 0, the average, or maybe 20, 25. So it's important. I anticipate it's about 14 degrees. But we will also make a simple calculation because it's very easy to compute what is the average temperature of our globe basing on the energy that we receive and what is the unique source of energy for the Earth system. It's sun. It's the only one. So the Earth system is closed in terms of energy, with the only inflow of the energy from sun. Okay, and then there is a corresponding outflow, of course, but this is the only exchange energy from sun that is received by the Earth system and may be released to space. But it's the only source of energy. So when you think, for instance, of fossil fuels are a source of energy. But originally, it came from the sun, because the fossil fuels are generated by vegetation, so ecosystems that grew up during the Paleo era, Paleo times, and this vegetation grew up thanks to the energy from sun. So basically, when we burn fossil fuels, we are using energy that was delivered by the sun like millions of years ago. And the same when we use solar energy, we generate solar energy by converting into electricity, for instance, the energy that comes from the sun. So by knowing, and you can easily find on Wikipedia, what is the amount of energy that the Earth receives from the sun during time, then you can easily compute the average temperature of Earth. So these numbers, I go back to my original reasoning, and forgive me if I jump sometimes back and forth, but I think it is also useful in order to keep your attention. So going back to my original reasoning, these numbers are important for getting prepared about the subject, and they are also important for passing your exam, because the quiz basically may ask you something related to these numbers. Again, the quiz will not ask you the precise number, like if I look here, global temperature increase 1.3, the quiz will not ask you what is the number. We'll ask you if the global increase of temperature is around 0, around 0.5, around 1, around 1.5, around or more than 5. And then you have to select. Okay, so it's important that you the idea that is between 1 and 1.5. You don't need to remember the precise number. Or like global CO2 emissions, and now we are about 35 billions of metric tons. Just remember the order of magnitude. It's not 1, it's not 300, is around 30. Okay, and again, it's important because I mean, not just for passing the exam. It's important because if you want to be prepared about a topic, you may get engaged in a discussion. And when you have to support your opinion, you have to demonstrate that you have a good knowledge of the numbers. Like politicians, you know, they often say the numbers. And when I release interview related to my research activities, I try to give numbers because it gives support to your preparation. I mean, if you're able to say the numbers correctly, because there are also politicians who say the numbers not correctly, and this is something that it's absolutely to be avoided. Better not to say anything when you are not prepared than risking of saying something that is plain wrong. But if you are able to give numbers, it means that you are prepared. Okay, let's move to the next slide then. Okay, let's discuss about some negative impacts of climate change. This is a quotation from National Geographic. So it's an important source of information. It's National Geographic is not really a scientific reference. It's a reference that is conceived for dissemination. The purpose of National Geographic is dissemination to the public. It's not really dissemination to scientists, but it is indeed an important reference. So Earth is warming up. And again, there is no discussion about this. So let's focus on what are the facts that are basically accepted about climate and climate change, and the facts that are being discussed and may be subjected to some controversy, because we already mentioned that climate change is also a controversial topic because it's extremely important. It has political implications, economic implications, and it's global. So Earth is warming up, no question on that. And humans are at least partially to blame. I think this is very correct. It's a very correct way of saying things. And sometimes we hear that the responsibility of global warming is humans. I don't think it is really correct because it's not accepted unanimously that, and it's not demonstrated. Besides being accepted, it's not demonstrated that the only problem is CO2 concentration rising up, and then it's correct to say that humans are at least partially to blame. There is no doubt on the fact that the human activity is at least partially to blame, because it's clear. If you get humans into a closed system, clearly the temperature increases. And with the increasing human population, clearly temperature over the globe increases, like also for animal activity. So I think it is a very correct way of stating it. The causes, effects, and complexity of global warming are important to understand. This implies that they are not completely understood, as I mentioned last time, so that we can fight for the health of our planet. I would prefer another word other than fight, because I think we should pursue the health of our planet. This is obvious. A fight, I don't like it because, the topic is controversial. It looks like for pursuing the health of our planet, we have to be engaged into a war, which is not really necessary. The important thing is if we want to fight for the health of our planet, and if we want to achieve sustainability, the important thing is education. Education in terms of scientific education and public education. So the important thing is to understand. And the reason is clear. you know, because if we don't get, for instance, people understanding the climate change problem, it's impossible to convince them to make an effort to resolve it. We need money for solving the climate change problem, and we cannot get people to spend money if we don't build their trust. And the same for science. We cannot achieve sustainability if we don't understand, from a scientific point of view, the processes. And you are here in this room for this very reason, understanding the processes. And sometimes it is a bit boring and nasty to understand complex systems because in some of the cases we have to admit the limit of our knowledge, which is nasty. It's something that is not stimulating. To conclude something like, I cannot explain this, it's not nice, it's not easy to be accepted. On the other hand, there is nothing wrong when we make scientific research, there is nothing wrong than accepting that a research question cannot be addressed today. Nothing wrong. In fact, when the founding agencies provide the money for research projects, they also accept that the project may fail because there is a limit to our understanding. Okay, so global warming impacts the environment in several ways, changes the seasonality of several natural processes, and has potentially negative impacts on the global health. So, what do you mean by changing the seasonality, and why changing the seasonality is important? Let me anticipate the last but one slide, I think. In order to give you an example, I would like to give examples because it helps to understand the concept. So let me jump forth, and then I go back for sure. And yeah, this is an example. And I am self-serving because this is a study that I recently carried out and published. And I am self-service because this is easy, but I could find many other examples. So this is an analysis of the drivers, the physical explanation. Physical, I mean laws of nature. So explanation based on the laws of nature of the Po River drought of 2022. 2022, the Po River went really to very low flows during summer, and it was a record. It was a record-breaking drought in terms of low flows, and it was a bit concerning. Actually, it ended at the end of the year, the drought came to a stop because there was intensive rain, and so the concern were in a bit mitigated. But still, there were concerns because people reflected, thought about what could happen if the drought lasted longer. And therefore, we made this analysis. It's a very simple one. I explained to you what the graph means. It's a very simple one. It is simple because along the Po River, we have observations starting from 1807, so about more than 200 years ago. And therefore, one can see whether the event of 2022 was unprecedented or not. And the way we did it was to look at the average flows in each year during 4 seasons. First, we look at the average flow of July each year. So the series is 200 years long. We got 200 values of average July flow. And what we assessed is that if we look at July, it is indeed a record-breaking drought. It is at the first position in the table. You see, and over the J column, J means July. And you see in the first position, 2022. It means that it was the worst drought in terms of low flow, average low flow in July along the full record of 200 years. And then you see the second position, the third one. Forget about the colors for now, okay? Second position, third position, etc. And then we looked at the average flow in June, July. JJ means June, July. Again, 2022 is the first position. And then we look at the average flow during May, June, July, MJJ. And then April, May, June, July, AMJJ. And you see that 2022 is always in the first position. Okay, but let's look at the graphs. The graphs depict the average flows in the 4 seasons, J, July, upper left, okay, JJ, June, July, upper right, and then May, MJJ, May, June, July, lower left, and then April, May, June, July, lower right. And what you see from the graphs, first of all, there are 2 lines, and the dark blue lines represent a moving average. So the light blue lines represent the observations, the average flows. The moving average is something that is obtained by smoothing the observation. Smoothing means eliminating the peaks and plotting average values. So what you see from the four graphs is that in July, you see a decreasing trend, upper left. You see a tendency going down. It means that in the past 200 years, the river flow in July is going down. But if you look at the bottom right, okay, April, May, June, July, you see that it's more constant. And here it's not plotted. If you look at the plot for March, April, you would see an increasing trend. What this means, it means that the flow of the Po River, in poor words, increased in spring, decreased in summer. Why? Because there is anticipated snowmelt over the Alps, and there is more rain during winter and less snow. And therefore, what we get, anticipated snowmelt, more rain, is an increase during winter of river flow. But then this river flow that is anticipated in winter, spring, is lacking during summer, because snow is like a natural reservoir of water. So if you decrease the snowpack, you have during the year the same precipitation, same volume of river flow, but it's anticipated. And this means that this natural reservoir is disappearing. This is a change of seasonality. So you understand how global warming may change the seasonality. Of course, in this case, it's very easy to be understood because it's clear to understand what is the effect of higher temperature on snowmelt. So it's easier, again, to be understood. But there are other changes in seasonality that are not so easy to be understood, which are relevant. And for the case of the Po River, what would be an action to mitigate this change? Let's suppose, first of all, that we need to mitigate the change, because there are cases where, we can accept the change because it doesn't impact much. So we could keep it and live with it. But let's suppose that in this case, this change indeed, in this case, for the Po River is causing some problems because we need water during summer, not during winter. And keep in mind that the Po River is providing water to about 1/3 of Italy. The Po River Valley is about 1/3 of Italy. And it doesn't only come the water that we use in the north of Italy from the Po River, it also comes from groundwater, but still groundwater is fed by the Po River. So I mean, it is extremely important, and it is a problem if we get less river flow along the Po River during summer. It is indeed a problem. And so what could be a solution? A solution is to replace the natural reservoir, the snowpack, with artificial reservoirs. So increase the number of reservoirs along the Po River course. They are already many. I mean, in the Po River catchment, in the Po River basin, catchment and river basin are two synonyms. So when I talk about a river basin, I could also use the term river catchment. Okay? So in the catchment, in the Po River catchment, there are already many artificial reservoirs, but they could be increased. This is a way to cope with it. Of course, it is something that has an environmental impact. Building a reservoir has an environmental impact. Okay, this is the example that I wanted to give. And let me go back then to our slide. And we were here. Global warming. So, global warming indeed has impacts, and let's keep into account that it's not uniform. And for instance, in mountain areas, global warming is higher than in the lowlands, and we don't understand the reason. We could, I mean, we could guess, we could make some guesses, but it's still not clear. And it's not clear, for instance, the fact that there are few glaciers over the globe. I don't remember which ones, but you can find the information easily on the web, that are increasing in size rather than decreasing. There is a general global trend to decrease of the volume of glaciers, of glaciated areas, but there are some few exceptions, and we don't understand why. And indeed, researchers are focusing on these exceptions, because understanding why these are increasing in size rather than decreasing may suggest solutions for mitigating the retreat of glaciers. The retreat of glaciers in general, I mean, it's something that occurred many times, and after the last glaciation, and we will talk also about the last glaciation, and the last glaciations peaked about 11,000 years ago. And after the last glaciations, there was a retreat. The retreat in general is something that is not necessarily concerning, but when the environment is heavily anthropized, and I'm not sure it is a good word, so it's mainly urbanized, it's mainly used by humans for resource exploitation. Of course, this societal organization, which is fit for purpose on the current state of the environment, needs to change if there are environmental changes. For instance, if we get less water than the Po River, from the Po River, we need to get more water from somewhere else. And therefore, our societal organization, water supply systems, need to be updated. So global warming is not uniform, and what is the impact? If I had to identify the main impact of climate change, I would say agricultural production. So food production. It is extremely important because, of course, if we say agriculture, we don't understand. If we say food, we understand it's important. And it is probably the sector that is more impacted. Why? I give you an example, because if you look at the global water consumption by humans, 70% is for water for food, is for food. So you understand why it is the sector that may be more impacted, because it is a sector that is tightly related to the environment, to the climate. And it's a huge sector. Of course, global warming is also impacting our daytime life, but we may put air conditioning on. It's relatively easy. It's easier to adapt for industries, for human settlements. For agriculture, it's a bit problematic, and sometimes it may require a change in the agricultural practices. And agriculture is huge. It's not easy to make a change. Of course, what I'm saying that the most significant impact is agriculture. You have to get it on average. There are, of course, places where the impact on agriculture is not a problem, like, for instance, in the north of Europe. They may also get some benefits for agriculture because a warmer climate means a longer growing season for agriculture. But they have other problems. So this is something that I'm stating with a global reference. And you have always to keep well into account that the effect of climate change, and in general, the effect of climate on human activities, is not the average. At the local level is varying a lot around this average. Other negative impacts of climate change, weather extremes, droughts and floods, basically. Okay, so we have the feeling that droughts and floods are increasing in severity after climate change. This is what climate models say. Actually, if we look at the data, it's more complicated, but the climate models, they agree in identifying a worsening of extreme events related to water, okay, under global warming. And it's not clear, even in the model results, it's not clear what is the effect on the memory of these processes. And let me be clearer. We observe from many observations that not only today, extreme weather events tend to occur in clusters. We talk about in hydrology of flood-rich periods and drought-rich periods. What is the reason? We don't know again. And we don't know why. But it happens indeed that the climate is subjected to cycles. I already mentioned the drought problem, and I now would like also to mention the flood problem. There are periods where we get a lot of floods. And of course, not everywhere. It depends on the locations. And this means that these processes have a memory. This is why in this slide I am mentioning the memory of climate and weather. And of course, we understand that climate has a memory. For sure, it has a seasonal memory, but there is also an interannual memory. So sometimes we get warmer periods, we get cold periods. And I just would like to mention that from 1960 to 1975-8, there was a concern, a global concern about global cooling because it was a cold period. And this is why people say, when I was young, there was a lot of more snow than today. And very frequently you hear people saying, but it doesn't snow anymore. Or when I was a child, we got a lot of snow because there was this cold period which lasted about 20 years. And if you look in Wikipedia for global cooling, you may see that also at the global level, there was a lot of concern, because keep in mind one thing, that we are concerned by global warming, but it's much more difficult to cope with a decrease of temperature than with an increase of temperature. And clearly, the history of humans says that. So the history of humans, if you look at the history of the Maya, and if you look at the history of the Romans, they increased in prosperity during warm periods, and they got crisis during cold periods. So there was a lot of concern in the 50s, 60s of the past century about this global cooling. And this is why if you search in Wikipedia, you find information on that. So when we talk about phenomena related to precipitation, so floods and droughts, Unfortunately, we have the problems that the observations are rare, in particular the observations of extremes, and so it's more difficult to confirm with data what the models predict. For temperature, it's much easier. With precipitation, we have reduced observations. And I think I need to better explain what I mean by reduced, because actually we have measurements or locations where we measure precipitation that are probably more dense than the location where we measure temperature. So it's not fully correct to say that we have less observations. To be correct, we should say that we have less observations in relation to the variability of the process. Rainfall is extremely variable in space and time. Temperature is not much varying. So if you have one thermometer in a region, basically it's enough. In a region, I'm not talking about an administrative region, like if you have in a catchment a couple of thermometers, one over the mountains and one in the lowlands, it's fine. For rainfall, you need many more measurements in terms of location where you measure it, because it is highly varying in space, in particular during summer, and it's also varying in time. So it's not just enough one observation per day. One observation per day, yes, gives to you the total rainfall in the day, but it doesn't give any information on the max intensity of rainfall, because maybe that the max intensity was concentrated in 10 minutes. But the moral of the story is that it's more difficult to confirm with data what the models predict. So, indeed, models say that there is an increase of the extremes. What is confirmed by data? What is confirmed by data is that there is an increase in some areas of precipitation, of rainfall. And if you look at the intensity, it is increasing the intensity of short-term rainfall, like hourly rainfall, rainfall that lasts for 10 minutes. For the rainfall of longer duration, like the rainfall that lasts for a couple of days, there is no evidence of increase. Now, I'm telling you one thing that you don't read on the screen, but it is a very nice example, in my opinion. If you think about recent floods in Italy, or also in other countries, but of course, I'm talking about Italy because it's relatively easier to find information. If you think the recent floods in Italy, we had many, really many. If you think at the type of the flood, you would find a striking feature. They are all small rivers. So we didn't get in Italy in the past 25 years floods from the big rivers. If you think about the Po, the Arno, the Tevere, or the Volturno, the biggest rivers in Italy, the Adige, there were no floods in the past 25 years. Maybe some high flows, but no inundations from these rivers. The inundations came from very small creeks, or maybe medium-sized rivers, but in particular, the inundation caused by excess of flood, of flow, excess of water, are really related to small rivers. What is the reason, in your opinion, for that? It is an interesting consideration. It's not a coincidence. The reason is that to cause a flood over a big river like the Po, you need a rainfall that lasts for 1 week. For the Po, you need a rainfall that lasts for 1 week. For a small creek, a rainfall lasting 10 minutes may be enough. And so the small creek is characterized by what we call flash floods, while the big river is characterized by a slow evolution of the process. And there is a hydrological, physically based explanation for that, but let's forget about the explanation. Let's take it for granted. So the fact that we have only floods in small rivers, and the fact that we know that in small rivers the floods are caused by rainfall with short duration, it means that what is changed is the rainfall of short duration. And what is typically an example of rainfall of short duration? It's the summer storm. You know that you experience during summer very violent storms. Maybe they last just for a couple of minutes, but in these 2 minutes you get completely wet. And what is instead the typical event, rainfall event in the November season is something that may last for 1 week. It's really boring because for 1 week it rains. It's different processes. So the summer storms, typically they last for a short time. And if you think at the date of occurrence of the recent floods in Italy, it's indeed mostly during summer. This is the rainfall that has changed. And indeed, the data confirm this. And these results showing that the data confirms an increase of short-term rainfall are very recent, just past 10 years. And they found at the global level such an increase. I think it is a nice example because it allows also you to understand the complexity of this. By the way, if you go to Wikipedia, and let me just, I think if I do Control N, perfect, Wikipedia, let me write in Italian, sorry. Wikipedia, lista alluvioni italiane. There is a nice page if you're interested, and sorry, I did something. Accetta tutto. Alluvioni e inondazioni in Italia is in Italian, but you know that maybe also there is an English page, but you know that you can easily translate nowadays, and it's an interesting. Okay, there are some warnings. When you go to Wikipedia and you see the warnings, please be careful because the warnings are extremely important, and it means that Wikipedia is a community created encyclopedia. And it means that it is subjected to review by the community. And when there are some concerns, usually they put warnings. Maybe that you know better than me, this fact. And these warnings are something that, for instance, in ChatGPT are not given and are very useful if you want to be rigorous. And it is very useful to go to the discussion that generated these warnings. These warnings are more frequent in the national languages rather than the languages that are more international. And the reason is that in the national languages, the review of the Wikipedia entries is slower, and it's also, it is something that is managed by a smaller community, and therefore there is more uncertainty. So be careful of the warning. In this case, I don't, by looking at it, they are not very important warnings. But anyway, this is something that it is interesting. And of course, when I said during summer, most of these floods, I said that they occurred during summer. First of all, you have to consider that when I say summer, you have also to refer to the geographical location, because the short-term storms, violent short-term storms in the south of Italy may also occur during winter. In Emilia-Romagna, it's more difficult. It's very difficult that here you get some thunderstorms with the noise of thunders, etc., during winter, but in the south it may happen. And also here, this is updated, and now we are in winter. So it's clear that you see the last references about floods that occurred in the fall season and winter. But if you go to summer, you see that there are also many examples. And these are interesting. Sorry. I went skiing during the weekend, so this is a reason for my voice. And these are, if you're interested in floods, it's an important source of information. Okay, next. Again, flood and droughts. This was the previous one, was weather extremes. I already anticipated by talking about the previous one about flood and droughts. So basically, we don't have much to say here. The only thing that I would like to say, because there is the bullet points refer to the consequences, I think they are self-explaining. No need to discuss why a flood or a drought is concerning. And the only thing which is interesting to emphasize here is within the red circle. So the mitigation actions, and flood and drought can be mitigated by non-structural and structural measures. What is the difference? Because when talking about climate change, often you listen people talking about black solutions, gray solutions, green solutions, or structural measures against nature-based solutions. So structural measures are also called black or gray solutions, means that to mitigate the impact, you decide to build structures like a dam. I talked about artificial reservoirs, and an artificial reservoir is a structural measure to cope with both flood and drought risk. Good. And what is the non-structural measure? It's also called the nature-based solution. It is a measure that is put into place, it is developed by using nature-friendly interventions, like, for instance, ecosystem services, like reducing the water consumption rather than increasing the water supply. Okay, so reducing the water consumption may be a way to cope with the lack or scarcity of water supply. And there is a long literature about nature-based solutions and also about structural measures. Today, there is a general trend in looking for nature-based solutions rather than structural measures. And the reason is simply the environmental impact, because basically with a structural measure, I mitigate the impact of structures by making other structures. So clearly, it is a bit concerning, because it's like a cat that bites its tail, you know. And on the other hand, there are some advantages. There are advantages in both solutions. What is the advantage of a structural solution? First, is more convincing. And, you know, nowadays, there is more transparency related to environmental planning, related to the use of natural resources. We want more transparency. Transparency means that you have to discuss a solution with the public, which is fine, it's perfectly fine, is what we want. But on the other hand, it also means that we have to convince the public. And the structural measure, with respect to people who directly suffered from an impact, is more convincing. This is the first advantage of a structural measure. There is a second advantage. The second advantage is that it is easier to quantify the benefit that is provided by a structural measure. For instance, let's again refer to water scarcity. If I need like 10 more billions per year of cubic meters of water, okay, and let's say 10 more millions, not billions, because billions is really huge. So 10 more millions of cubic meters of water per year, then let's build a reservoir with a capacity of 10 millions volume of water. It's very easy. If we instead decide of reducing water consumption, how can we measure how much water is saved if we tell the public of closing the tap while brushing your teeth? Or more, if we tell the public, please don't use water, potable water, drinking water, for irrigating the garden. How can we measure how much water is saved? It's impossible. We have to test. So we make a public campaign of information, and then we test it. But you understand that one thing is to make sure that I have 10 more millions of water available by building a reservoir, 10 more millions of cubic meters of water. Another thing is to guess that we may save 10 millions of cubic meters of water. If we are in the urgency of solving a problem, it's problematic. And I made an example that is very easy. There are other examples like ecosystem services. It's impossible to quantify the benefit. And another example that I could give to you, there are several experiments ongoing to treat wastewater with ecosystem services. It means that instead of using a wastewater treatment plant, which has a huge environmental impact for many reasons, what we are experimenting is to release the wastewater in artificial basins close to the cities and put vegetation into these artificial basins, and in order to treat the wastewater with ecosystem services. This is much more environmentally friendly. And then this wastewater, once treated, is released in the ground directly. Big question, is it effective, the ecosystem service, in cleaning the water? I think they are leaving, so just let's wait a little bit. And are they effective in cleaning the water, these ecosystem services? What people are doing is to test it. So they go there periodically, make testing on the state of wastewater. They measure some water quality indicators. And when they are satisfied, when the water quality requirements are satisfied by these indicators, they release the water in the ground. Otherwise, they cannot release it. And there are many projects dedicated to this, but again, it requires testing a long time. It's a bit risky. It's a bit risky. So this is why there is a strong debate about structural measure and non-structural measures. So my interpretation, it depends on the urgency of the problem. If we have time to test nature-based solutions, for sure it is better. But if we don't have time because the problem is urgent, it's maybe structural measures are needed. For instance, to give you an example, I think that you know that there is, after the flood in the Romagna region that occurred in 2023, people are thinking about mitigating the risk of flood in that region. And I believe that for some of the cases, there structural measures are needed because it's problematic at this stage to solve the problem only with green solutions. Okay, hurricanes. I make a long story short by reading from two quotes from NASA and IPCC. Two very important sources of information. What is NASA? I think you know it. It's the Spatial Agency of the United States. IPCC, we will discuss it in a moment. It's the Intergovernmental Panel on Climate Change. Is an organization of the United Nations that is in charge already starting from, I think, 20 years ago, more or less, is in charge of studying climate change and proposing solutions. IPCC is very conservative in the interpretation of climate change, meaning that it's about skeptical. They predict that climate change will worsen and will become an important problem. And NASA more or less along the same line. And even if you know that in the United States now the wind is changing direction, maybe then that it will change again in the future. So in the United States now there is less funding for climate change research because they have an economic crisis, and the current government, as you know, decided that climate change is no more a priority. So from NASA, climate models predict hurricanes will likely cause more intense rainfall and have an increased coastal flood risk due to higher storm surge caused by rising seas. Additionally, the global frequency of storms may decrease or remain unchanged, but hurricanes that form are more likely to become intense. NASA, IPCC, which is extremely, as I said, skeptical, conservative. Globally, there is low confidence in attribution of changes in tropical cyclone activity to human influence. This is 2013, so it's already a bit outdated. This is due to insufficient observational evidence, lack of physical understanding of the links between anthropogenic drivers of climate and tropical cyclone activity, and the low level of agreement between studies as to the relative importance of natural variability and man-made forcing. I think this explains perfectly the overall meaning of the discussion that we had so far. Limited knowledge, limited evidence, etc. Hurricanes are extremely important in some regions of the world. It's an extreme weather event that is causing a lot of impact. In Italy, it's not so important, but still also in Italy, we have some problems. But our knowledge of the impact and generation of hurricanes and attribution to climate change is still limited. Don't get concerned, because the fact that the knowledge is limited doesn't mean that there is no solution. There is always a solution to a problem, always. And of course, the solution must be identified based on our knowledge. But if the knowledge is limited, it's no problem at all. We humans are used to deal with limited knowledge. Also, when we plan for economics, in economics, we have a limited knowledge of the mechanisms. Just to open a parenthesis in economics, which is also much related to climate change. As I said, we don't discuss much about economics in relation to this subject on science of climate change. But indeed, there is a strong connection between climate change and economics. I would say that economics is really an important driver. So basically, in order to make a consideration about economics, you know that we are currently in a period of inflation. Actually, I heard a speech by Mario Draghi some time ago. You know, Mario Draghi is much expert about economics. And he said, this is something that we did not predict. And he was admitting a kind of responsibility. He said, we were convinced that the increase of inflation would not occur this time. And we are still in the progress of understanding why it occurred. So even when we talk about the market, it's difficult to understand what's going on. This is an example. I give you another example. As I said, I went skiing in the weekend. Actually, I go skiing or in the mountains all the weekends. So past weekend, traveling from my destination, my usual destination, to my home, which is close by here, I found a lot of traffic. 4 hours I took of driving time with which means 1 hour more. Yesterday, same conditions, better weather, and the end of the Olympic Games, I predicted that traffic would be dramatic. Actually, yesterday, no traffic at all. And I sometimes speak with my colleagues working on transportation engineering, and they say it's unpredictable. It's really unpredictable. Statistically, we put the black days or red days, the bollino rosso, the red points in some days of the year. So, I mean, the weekend of December 8th or August 3rd, statistically, we put a red bullet. But they say, but how many times we experienced the 1st of August, no traffic at all? And he said, the explanation may look simple, like with the warnings, people didn't travel by car, but actually, it's not so simple, because usually we find a lot of people driving the August 1st, and occasionally it happens, unpredictable. So, if we cannot predict economics or the traffic, you understand that even predicting the climate is difficult. We can predict the weather, and in the weather we made a lot of improvements, but the climate, which means predicting with a lead time of so many years, it's more problematic. Okay, close the parentheses and examples. Let's move forward. And sea level rise. This is another important topic. And in particular, it's important the order of magnitude. Remember it, because I think I already mentioned this. Sometimes there is a trend to exaggerate the magnitude. So, what is the sea level rise that we experienced since we started measuring it? So since 1880, it's so far about 20 centimeters. It's not uniform, because we think of the sea level as something that is uniform over the globe. It's not uniform. Why it's not uniform? For instance, because gravity is not uniform. Gravity itself. I learned only a few years ago that gravity is not uniform. So gravity is not uniform, there are tides, and therefore sea level rise is not uniform. And if we talk about the past 30 years, it is significant because starting from 30 years ago, we have a lot of measurements of sea level by satellites. In the earlier years, we only relied on direct measurements. So if we look at the past 30 years, it's about 3.8 inches, which means about 10 centimeters above the 1993 levels. But actually, if we look at the overall progress, there is no clear tendency, no clear trend, also in the past 30 years. It is accelerating a little bit, but not that much, okay? So, and if we talk about predictions by models, because now in this slide, I'm talking about observations. If we talk about prediction by models, what do the model predict? I give you an order of magnitude up to 2100, so 74 years from now. The models predict an additional sea level rise in the worst conditions about additional 70 centimeters. But according to the average prediction, it should be around plus 40 centimeters. So it's not meters, what I mean to say, okay? So if we talk about sea level rise, we should talk about tens of centimeters, not meters. Still, as I mentioned, I think already to you, it doesn't mean that it's not relevant. It's also relevant, 30 centimeters, especially in terms of saltwater intrusion into the land. In fact, if we read on the left side of the slide the negative effects, there is salination of coastal waters and destruction of coastal ecosystems due to saltwater intrusion. Saltwater intrusion is a big problem for coastal areas. It means that groundwater gets salted and therefore no more usable for drinking purposes. Good. Positive impacts, this is also important. We shouldn't forget the positive impacts, and the map shows the change in agricultural productivity between 2003 and the predicted agricultural productivity in 2080. And where you see red or yellow, there is a decrease. Red is larger decrease than the yellow. When you see light green, very light green is a very small increase, and when you see increasing darkness of green, it means a large increase. And the map shows what we could expect. So where there is a lot of water, in the countries where there is a lot of water, agricultural productivity may increase, and especially it will increase a lot in the countries where they will get also more land that is prone to cultivation. So Canada, Norway, Sweden, Finland, but also for Italy, it is predicted an increase. And indeed, this is an example of potential benefit of climate change. There is less mortality for cold waves. And I spoke with a colleague that is a medical doctor, and he was involved in our research about the impact of climate change. And then we showed some statistics on the increase of mortality during summer due to cold, hot waves. And he told me, remember, the statistics are clear. People die during the winter, not during summer. And this is something that I never thought about it. So he said, yes, you get increased mortality during summer, but in summer, mortality is low. So an increase of mortality in summer is not significant. I mean, in statistical terms over the whole reasons of mortality. And then he said, look, this is a confirmation of the fact that people die during the cold weather. And then he said, look, if you look at the decrease in mortality during winter, it overcompensates by a large amount the increase of mortality during summer. And also he said, you know, when I look at these predictions don't take into account that the average duration of the life expectation is increasing a lot. So indeed, the human activity is causing some climate change, which cause the death of some people. But the human activity is also reducing mortality a lot. And by the way, he said this is a problem because the global population is increasing and also increasing in age. So it is, societally a problem. And he said, you know, when you talk about the impact of climate change, you should make an overall assessment. He said, climate change is a necessary consequence of human development. And then human development gives advantages and disadvantages. He said, the important thing is that when you make a balance, when you make a comprehensive evaluation, the mortality of people is reduced. And indeed, this is something that impressed me for, on the one hand, the very trivial consideration that people die during winter. I could expect it, but I didn't know the data. And on the other hand, the less trivial consideration that indeed, when we look at climate change, we should also look at it as a necessary consequence of human development. And this is necessary. I mean, we cannot avoid it. We can mitigate climate change, and then we should make a cost-benefit analysis, like we do for many other planning procedures for ensuring sustainability. Okay, so decreased avalanche risk in some regions. This is something that during winter is very popular, and it is indeed a great risk, and it is decreased because with less snow. On the other hand, risk is also determined by the number of people who go over the mountains during winter. And indeed, if you look at the deaths for avalanches recently, there is an increasing trend. And the farmers, we already talked about it, and also crops and crops that grow better. Tourism, they benefit from a longer season. I wrote, but not skiing, which is, of course, something that it was my idea. Actually, I talked with some people recently working in the ski resort, and they say, look, with artificial snow, we are earning more money than in the past when we had worse weather, limiting the number of skiing days. And they adopted a slogan, which is something that made me like amazing. The slogan is, let's hope that it doesn't snow, because it means that it's sunny days and we can make artificial snow. I was not happy of this slogan and also about the overall consideration. I was not happy. But again, it's something that gives to you the idea of the complexity of the problem. Shipping commerce, you know now, the interest in Greenland. The interest in Greenland is due to climate change, and we know that. Because indeed there are benefits. And then regions that were not interesting before the glaciation now become interesting. I mentioned to you the IPCC. So the IPCC is, let's try to click here. Here there is everything. Now, message. If you are interested in learning more about climate change, this is an essential reference. And in particular, if you look at the reports, I click here, you see that they have a lot of reports available, and they talk about the 6th assessment report. They have a mission, and the mission is to publish with some periodicity, and I think the periodicity is more or less around 3 years, assessment report about climate change. The last one is the number 6. And there is a lot of information. And these reports are very, long to read, but there are some syntheses. For instance, the physical science basis is probably what is more interesting for us because it talks about science. It talks about mitigation in with an approach that comes from physics, not from engineering. So mitigation doesn't mean structural or environmentally friendly solutions. It means reduction of CO2 emissions. It talks about the impact, and there is a synthesis report. The synthesis report is not much long. So if we look here, let's see, read the report. Many clicks are needed. Summary for policymaker is very short, like few pages. And then there is the longer report, but it's still a synthesis. There is a presentation. There are figures, press release. It's nice, a lot of information. As I mentioned to you, when you get an information and when you refer to something, IPCC, something we are referring now, we should get an idea of the position of your reference in the international debate. In a debate, there are, by definition, several positions. And IPCC takes a position that is very conservative, as I mentioned to you. So it is to be conservative, assuming that indeed the problem is urgent and we need a urgent solution. There are other possible references, which I leave to you to search, which are which have a different position. The IPCC has an advantage that is usually well taken by, let's call it the system, the governmental system, because the IPCC is an emanation, it's an organization of the United Nations. And the IPCC is including a lot of renowned scientists which have different opinions. So it is something that it's a reference that is often well taken. It's very important. Okay, it's not very. I mean, it doesn't give the solutions. It doesn't take an approach from engineering. Engineering means finding a solution. In my interpretation of the engineering term, it doesn't say. It doesn't give a guidance, a technical guidance. It gives a scientific guidance. Okay. It is interesting to discuss what is the difference between a scientist and an engineer. And sometimes I just reply by saying that it's a nonsense to make a difference because there can be engineers that are also scientists, and there can be scientists who are not engineers. So it is not really meaningful. But indeed, we can find some differences in the perspective. And to say some that is also a bit fun, fun, I mean a lot of fun. I mean a lot of fun. I could say one difference that indeed I often see. The engineer usually is used to take the responsibility of what they say. Why? Because it is attributed by law. An engineer, when makes a design, a technical design, put the signature. If the design is wrong, the engineer can be charged, have a civil and penal responsibility, civil and criminal responsibility. The scientist is not used to take any responsibility because he is not subjected to any responsibility because science can be wrong. And this is a big difference because the scientist, it is not much concerned by a wrong theory, a wrong explanation. It is more concerned by being conservative. So the science, if is in doubt, usually takes the option of being conservative. The engineer, it's a different thing because if you are too conservative, you are anyway wrong. The engineer is anyway wrong if it is too conservative. And therefore, usually the engineer is less conservative with respect to a scientist. And the difference is the attitude of the engineer to take a responsibility of what they say. The scientist has not this attitude, but not for lack of responsibility. It's just for a different setting, operational setting. But again, I think it's a nonsense discussion. Let's forget about IPCC and let's look at what they say. And this graph is very popular, very, very popular. And I think it is maybe too popular because it's not very meaningful. And I explain to you, first of all, what is the graph displaying. I'm sorry that it's not very clear on the screen, but anyway, you have the slides. So what you see in the left-hand side is global warming from the year 1 reconstructed up to 1850 to the year 2020. And you see that the global warming that we are experiencing today is unprecedented. This is something that we already knew. And we already knew that indeed, if you look at the past 11,000 years, or maybe the past more than that, the past 500,000 years, the Earth never experienced a so rapid warming. But if we go back further in the past, we can find the natural oscillations which were even more rapid than this one. But still, I mean, this graph is very meaningful. And this is prediction, not real prediction, sorry, simulation by models. This is observations plus reconstructions. And this is a reconstruction by model with two options. The lower reconstruction, the one that looks flat, is simulated by models without accounting for CO2 for human activities, CO2 emissions by humans. So if we don't plug into the models the CO2 emitted by humans, we get a flat simulation, which is not reproducing the recent warming. Instead, if we plug in the increase in CO2 emissions from about 1880, industrial revolution, we get an increase of temperature. And this increase is increasing than the observed. So this is a confirmation that the reason why climate change is attributed to humans is model simulations. We already mentioned it. So this is a very popular graph that is used to prove that climate change is human-induced. Actually, we should never forget, we already discussed this, to say that this is models. And unfortunately, if you look at the capability of models to reproduce the past oscillation of temperatures, and even more than that, rainfall, we see that in reproducing the past, they are not very effective. And this should be kept in mind, because, of course, we should keep the debate open about the causes of the current climate change and the global warming. It is very important that we keep the debate open. Because if we close the debate, like saying we are that sure it's the increase of CO2 emission that is causing it, and only that, then we close our eyes, we exclude other possible solutions other than the reduction of CO2 emissions. And it is extremely important instead that we keep our mind open. Like in science, we are used to do. In science, we should always keep the doubt that theories may turn out to be wrong, because theories reflect our current understanding. If we look at the past history of science, we find a lot of examples of theories that were believed to be true, and then were proved to be erroneous and were corrected. Anyway, this graph is very popular. Now, here there is another interaction, and I think the interesting thing of this graph is the figure, which shows the costs of climate-related disasters in 2022, and you see that there is the drought in Europe at the second place. The first position is held by the hurricane that occurred in Cuba, Hurricane Ian, Cuba and the United States, and then there is the European drought, floods in China, a drought in China, and floods, etc. Basically, what you see is most of them are related to water. They are water-related disasters. And indeed, if we look at a progress in time of the costs, the impact of water-related disasters, this is much increasing. There are interesting data provided by, let me just open another one, Munich RE. Munich RE here it is. Munich Re is a reinsurance company. They provide insurances to insurances. It works like this. The insurance company needs also to be insured, because if they get a disaster, they have to give a lot of money to people, and therefore they get insured against possible failures. And Munich Re is one of the most popular reinsurance companies. They provide, again, insurances to insurances. And if you go to the website, they have a lot of interesting data. And we are not exploring it now because we need some time. And you see, this is now they refer to the Italian part of it. Let me see. I would prefer to go here. Okay. So you see, for instance, now a news, resilient global economy, growth expected to remain virtually unchanged in 2026. And here there are several information, and you can find also data about the impact of natural disasters. And let me see, probably they are in insight or under risks. Okay. And here there is, you see, natural disaster risk, rising trend in losses, and a lot of links, and there are a lot of data. I'm not exploring anymore, but what I wanted to say is that this graph here is taken by Munich Re. Okay. And so basically, here, the answer to the question about the reasons why the cost of natural disaster is increased is this one. It is not clear if the increase is caused by global climate change rather than the increased value of human settlements, because the risk, the impact is measured in terms of economic losses or losses of intangible assets like the human life. And they are increased, but it's not clear, for instance, if the increase of human losses is due to increasing human population rather than increasing flood frequency. Because if we look at the frequency of the floods, it's not clear whether it's increased or not. What is clear is that it's increased the impact. For instance, if we look at the impact per capita, then the tendency is more or less stable. The trend is stable. Okay, next. I think we can basically skip this discussion because we already talked about uncertainty or limit of our knowledge. There is only one thing that I would like to say more about uncertainty. I already said that uncertainty is not a problem. Limited knowledge is not a problem. We can anyway find solutions. If we are uncertain, the solution to uncertainty is its quantification. The worst thing is to be uncertain and to not know the amount of such uncertainty. So if I am in doubt about something, the first thing that I do is to try to quantify a likelihood of my doubt, like tomorrow, will it rain or not? Maybe 10% rain. Now, if I have this quantification, it's not a problem. I'm still uncertain, but I have quantified it. If I have no clue, this is a problem. So related to climate, it's not a problem to have a limited knowledge if we can, in a way, estimate what is the impact of this limited knowledge. If I have no clue, it's a problem. Okay, this is the only thing that I just want to say about uncertainty. And just keep in mind that when the process is chaotic, uncertainty is unavoidable. Butterfly effect. You remember about the famous say, I think it is attributed to Lawrence, who said that butterfly flapping the wing in Japan may cause a tornado in the United States. This means that there is a chaotic behavior. A small change in the system, in the Earth system, in a place, can originate a striking, huge impact in another place. This is chaos. And in these conditions, uncertainty is unavoidable. Just the important thing is to estimate it. Now, let's make the break now. We will meet again at 3, and we will start from here. Okay, thank you. I am skipping this last slide, which is related to something that we already discussed about the nature of science, what is the purpose of science, and the graph reports a list of the milestones, what we identify as milestone in climate science. I think it is self-explaining, so I am skipping it, which is actually the last one, because the next one is what we already discussed about the Po River. So let's move forward then with the next link, the next supporting document for our lectures. If you have any questions so far on what we discussed, I invite you once again to not hesitate to ask me. So, second link, I think I have a slide, PowerPoint, 1 second. Yes. This is the PowerPoint that can be downloaded from my website. Let me just check the chat 1 second. I want to see, okay, nothing new here. And let me get okay. This is this lecture, this supporting documents is related to a more detailed discussion about the climate change problem, and in particular regarding climate change attribution. Attribution means identifying the drivers, the causes of climate change. And in particular, we'll discuss about the history and science of climate change and the impact of uncertainty and the data that we can use with particular reference to open data. There are some parts of this lecture that have been already discussed by me. And of course, in this part, I will jump straight to the conclusion, or will skip them. So let's start from the evidence by making 3 examples. And the examples which I would like to start with is related to the figure that you can see here. There are several of these figures available here. I mean, in the center of the slide, the picture that is showing the retreat of glaciers with a sequence of pictures taken in the same glacier at the Svalbard. So it's clear that global warming is there. We already discussed it, and it's an evidence. And it's also an evidence of the fact that the impact on the water cycle is important, and in particular in terms of seasonality of water resources. The figure on the right, on the upper right part of the slide, refers to the Po River Basin. It is a 3D representation of the Po River Basin, with some numbers giving the water balance. The numbers are not important at this point in our discussion. Just important to emphasize that the change in seasonality has any impact on the water balance, and in particular on the seasonal water balance, which means that the balance may not be closed in some seasons. And what does it mean that it's not closed? It means that there is a lack of water, and it's lack of water for humans, in particular for food production, as I mentioned, Another example is given by the overall series of the annual minima for the Po River and Ponte Lagoscuro. Ponte Lagoscuro is the last measurement station in the Po River, where we measure the river flow. Ponte Lagoscuro is close by, is close to Ferrara. And you see that there is a slight decrease. This figure refers from 1920 to 2009. There is a slight decrease. It is a decrease that is affected by some variability. So the trend estimation here is uncertain for the presence of a lot of variability. But if we just look at the trend is decreasing. Again, this figure anyway shows the importance of distinguishing trend with respect to variability. So change with respect to variability. And in this particular situation, the large variability is in a way making the estimation of the trend a bit problematic. If you exclude the years of the big drought that occurred in the first 10 years of this century, then you see that probably the trend will become something like a stable situation, a stable state. Here on the bottom right of the slide, you see a representation of El Niño southern oscillation. El Niño southern oscillation is inducing a lot of climatic impacts in a large part of the globe. And El Niño southern oscillation is something that we cannot predict. So it gives to you further emphasis on the uncertainty that is related to climate predictions. All of these things, climate change, possible impacts, are related to sustainability and sustainability of human development, which is, an important target of the Agenda 2030 of the United States. 2030 is about to come, and sustainability is what motivated issuing the Sustainability Development Goals, which are an important driver by the United Nations that is given to government, that is given to international organization. It is particularly interesting to look at these issues, these international suggestions, international guidelines, in light of the recent developments, and in particular of the recent geopolitical tensions that you know very well, because they are on the media, which changed significantly the priority that is given at the international level to sustainability problems and climate change. In fact, also climate change and sustainability are much related to geopolitical drivers, which are very difficult and complicated to predict. You may just think at the targets that we fixed for decarbonization in Europe at the global level, and these targets are continuously being revised. Like also the Green Deal of the European Union is being revised because, for instance, the target of shutting down the circulation of cars that are fueled by diesel engines, it's being revised because the plan was just to shut down them from 2035, and recently you may have heard that this deadline was reconsidered because, of course, there is also this kind of unpredictability of the geopolitical situation that is introducing a further element of uncertainty. So these are some examples of unsustainable impacts of societal developments. we already discussed many of them, so CO2 emissions and fossil fuels, construction of hard structures like river dams, river barrages, and also the development of intensive agriculture. These are all developments that are also related to human development, to the progress that we are making towards achieving welfare at the global level. But on the other hand, there is this impact. And the message from this slide is that we should consider that climate change is, at least in part, not due to bad will, but it's, at least in part, due to goodwill. And the goodwill is to increase the level of welfare. And therefore, this implies that reaching a solution, solving the problem, has also an impact in terms of welfare. And this impact is larger for the countries and the people who are less advanced in welfare development. So the countries, the poorest countries, the countries with low gross domestic products are those that are going to experience the larger impact from climate change mitigation and adaptation. This is something that we really need to consider because, and I understand the reasoning is a bit complicated, but if we don't increase the welfare at the global level, there will be, it's unavoidable, an impact on the geopolitical tensions. If we take decisions in order to make sure that the progress is sustainable, that are impacting on the welfare of some countries, we have to expect the surge of geopolitical tensions with these countries. And this in turn is influencing and is undermining the effectiveness of our efforts towards sustainability. And this, again, vicious circle is to be carefully considered, because if we give an acceleration that is not justified to climate change mitigation and adaptation, because we want to be conservative, which is a commendable action, to be conservative, which means accelerating, but a too fast acceleration may, at the end of the story, undermine the effectiveness of the action itself. So, in a way, to try to be more gradual in getting to target may be the most effective solution. Accelerating too much is not really the right solution, in particular if this acceleration is imposed by the top with a top decision, and it's a decision that is generating concern and some bad humor in people. This is something that in principle should be avoided. Of course, in order to get to target is necessary an understanding of the complexity of these links and feedbacks between different systems. We start from science, but of course, our knowledge, if we want to become experts, if we want to be effective in proposing solutions, should be extended also to international politics, to the international rights and market dynamics. These are all systems that need to be connected to the climate and societal system. Very often now we connect only climate system with the societal system, with a limited view of the societal system that focuses on CO2 emissions without focusing on the impact that the reduction of the CO2 emissions may imply, because, you know, decarbonization is really costly and it can be should need to be imposed at the global level, otherwise it's not effective. But on the other hand, who is going to pay is who is going to pay more in relation to the gross domestic product are the countries with the low gross domestic product. And therefore, if we ignore these connections, if we ignore these relationships, then the overall action risks to be not effective, and the risk is also that the geopolitical tensions are increased, which is something that we need to avoid, of course. Okay, now we already defined weather and climate, and therefore we don't need to redefine it again. What is another important message delivered by this slide? First of all, it's interesting to look at the graph on the right side. It's reporting the increase in temperature in some big cities. And you see that, I think I have a slide, let me check, yes, on the Heat Island effect. You see that in the cities, the temperature is increasing much more than the global average. This is something that needs to be considered because people live in cities. And therefore, even if it is a phenomenon that is isolated geographically because it's only located in the big cities, still it is affecting a lot of people because these are big cities hosting a lot of citizens, and we will see what is the explanation, the physical explanation of this larger increase. But on the other hand, this increase concentrated in the cities gives also a confirmation that the warming can be indeed human-induced. In the cities, it is for sure human-induced, and is not necessarily global. And is not necessarily caused only by the increase of emissions. We will see what is causing the increase in the cities. And the other important message that is delivered here, besides the definition of weather and climate, is about statistics. The message is, if you want to understand climate and climate change, the underlying science for understanding are physics, for sure. Physics, because climate is regulated by the laws of physics, and in particular, conservation equations. So conservation of mass, conservation of energy, conservation of heat, conservation of momentum, which means forcing. These are laws of physics. So to understand climate, we need physics. No doubt on that. To some extent also chemistry, less important. And there is another science that is extremely important, I would say same importance as physics, which is statistics. Because in the presence of randomness, randomness means uncertainty. In the presence of randomness, we need a science that allows us to deal with randomness. Randomness is given, for instance, to chaos, to complexity. Randomness is there. Okay, it is there. We need a science to deal with randomness because we cannot take randomness as something that is just unpredictable. It's not true that it's unpredictable. When I toss a coin, I can predict that it is either head or tail. So it is predictable. It is completely random, but it is predictable. It is not predictable for sure, but it is predictable because if I can say that it's either head or tail, it's predictable. So what is a science, a candidate science to deal with randomness, to be able to predict randomness? There are several solutions. And these solutions can be all included into the big umbrella of statistics. And what are these several solutions? I give you some ideas. Fuzzy logic, machine learning, artificial intelligence. It's part of statistics. Artificial intelligence, it's statistics. And probability. The most classical way of dealing with randomness is indeed probability. We can use artificial intelligence, fuzzy logic, something that is probably more attractive. But we have to take into account pros and cons of these solutions. What is the pros, the advantage of artificial intelligence? It's easy. It's very easy. And we mentioned earlier, Wikipedia versus ChatGPT. It's much easier, ChatGPT. I am using ChatGPT a lot for preparing my lecture, for not only for ChatGPT, Copilot, Gemini, for preparing my lectures, for doing my research. What is the disadvantage of artificial intelligence? The disadvantage is that it can be wrong. It can be plain wrong. And therefore, we have to make sure, if we use it, to check, to make the checks. And it's not easy to make the checks. We need a lot of additional clicks, follow the references, make a study. Many times I was redirected by ChatGPT or Gemini to a paper to support what ChatGPT was saying. And by reading the papers, I realized that ChatGPT just took it wrong. So this is the disadvantage of artificial intelligence, which shouldn't be called artificial intelligence. It should be called aided search. But this is the disadvantage. What is the disadvantage of probability? It's very boring and it looks complicated. It's not complicated, actually, but you realize that it's not complicated when you studied it. Because at the beginning, it looks complicated. What is the advantage of probability? It can provide rigorous testing. So if you adopt a probabilistic method, you can check if it works, because probability is based on a very rigorous theory, which makes it boring, but still, it's very rigorous. So you may wonder why I'm saying this. I'm saying this because we will not use any probability in this course. But I really would like that you get it, the message, which is, if you want to study climate in a rigorous way, you cannot avoid probability, applying probability laws together with physical laws. And the best thing is if you can justify probability with physical arguments, with arguments from physics. This is the best solution, because you provide a rigorous testing through probability with some very credible justification, like I'm using this probabilistic method because the conservation of energy is affected by uncertainty for these reasons. Okay, but the message is that as a student, you, as me when I was a student, probably don't like probability. I didn't like it. Absolutely, I didn't like it. But at the end of the story, I got that if I wanted to study water cycle, if I wanted to study sustainability, and then the implication, which is climate change, I came to climate change science by implications, because I am a water scientist, basically not a climate scientist, as I mentioned to you. I realized that I needed to study probability. And the result was that now I think I have a fair good knowledge of probability theory, and I found that it's not boring. But after I studied it at the beginning, it was something that it was not easy for me to understand. And I got the feeling with probability thanks to very good teachers that I had after the university during my PhD. And therefore, this is why I want to be clear with this message. I really would like to make you aware that if you really want to look at climate in a rigorous way, you should base your consideration on physics and probability. It doesn't mean that you have to make research on it, just that you don't have to avoid it just by a wrong assumption that is something that you don't need. Okay, so the importance of statistics. Now let's look again at the cities. This is a nice figure of what is the urbanite island. And here you see a quote from one colleague who performed a very nice, simple, but very nice analysis of warming cities. He just took public available data, and this paper was cited a lot of times. And he gained a lot from his career as a researcher from this very simple analysis. Another message to you: don't think that for making discoveries you need to be a top-level brain. Maybe that you are a top-level brain, we cannot exclude this, but what you really need to make discoveries is to have creativity, ideas. And sometimes it's very simple. I could make to you a list of essential scientific discoveries, including the relativity theory by Einstein, who didn't require really outstanding brain. They were relatively simple. But of course, sometimes also simplicity is a key ingredient of a great discovery. Sometimes simplicity is an ingredient of an outstanding brain, the capability to identify simple ideas. So this was very simple. He got public data, temperature observed in cities, and showed that in cities with more than 5 million inhabitants, where most heat-related fatalities occur, by the way, during summer, the average change is about 0.3 degrees per decade, which means that some of the cities have more than the mean, like 0.6 degrees per decade. It means 0.6 degrees every 10 years, which means that it's more than 2 degrees in cities, with some of the cities reaching, like, if you go back to the previous one, if you look at the yellow city, is Tokyo, from 21.5 to 24.5, more or less. So 3 degrees. And it was very simple. And the urbanite island effect is not only related to CO2 emissions. Part of it is related to global warming, that's fine, but the additional part is just given by increased reflectivity, reduced vegetation, and increased urbanization and air conditioning. All of these effects that appeared starting from about 25 years ago. Now, this is the graph is related to, it's taken by our Worldin data. CO2 emissions per capita versus gross domestic product per capita 2018. CO2 emissions on the vertical axis and the gross domestic product, what is called in Italian prodotto interno lordo, in the horizontal axis. What you see is that the decrease in gross domestic product, there is a clear increase starting from gross domestic product per capita of about $5,000 US dollars. There is a clear increase of emissions. And this graph is a demonstration, a very clear demonstration that the CO2 emissions are related to the gross domestic product, which means that, you know, decreasing the CO2 emissions without decreasing the gross domestic product is really a challenge. So the CO2 emission, the increase of CO2 emissions was motivated by the increase of the gross domestic product. Another thing that should be clarified when discussing climate change, in order to decrease the controversial part of the debate, is that often there is the implications that politicians don't want to reduce the emissions, don't want to contrast climate change. It's not a matter of will. Sometimes it's a problem of having no other choice. And this should be kept in mind, because one thing is the bad will, another thing is the lack of solutions. So a recommendation that I sometimes give to colleagues when we discuss these things is, please don't take an against attitude. Don't stand up against something. Propose alternatives, propose solutions. This is the way to find solutions, actually, and to manage a debate. The debate is efficient if it provides at the end a solution. The debate may also be controversial. It's not a problem, but if it provides a solution. Otherwise, if it remains only a controversy, this is a bit of a problem. Okay, so what are the drivers of climate dynamics? Let's get more into science. The drivers are solar irradiance, because it's the only source of energy for the Earth system. Another driver is greenhouse gases, because greenhouse gases, according to the greenhouse theory, they limit the flux of heat from the Earth to the space. Therefore, the Earth, the solar energy remains trapped into the Earth system. It's not only greenhouse gases, it's also the concentration of aerosols, dust, smoke, and soot. These are also important. In both directions, the concentration of aerosols can also cause cooling. What is solar irradiance? It's the power per unit area, so surface power density, received from the sun. It is usually measured in watts per square meter in the unit of the international system. Keep in mind that we know that the sun has some cycles, and in particular, there is the 11-year cycle that we deciphered, identified. And still, there is a lot of the solar dynamics that we still don't know. And also, the measurements of solar irradiance are affected by uncertainty. Not really, uncertainty doesn't really impact on the average, but in terms of impact on the day-to-day measurements, it's very important. If you are interested, global maps of solar irradiance are available at the Global Solar Atlas by the World Bank. I click on this link in a second. Let's look at the link, at the Wikipedia link, describing solar irradiance, because I hope that we can find the value here. You don't need to memorize the value. Let me see if I can skip this. So I really don't like that it opens in let me copy the link if it's possible. Okay, not possible. So let me do this. 1 second. Okay, good. Solar irradiance. We already defined what is solar irradiance, but I want to see if there are values here. Okay, types. Here there are the maps, which we will see in a moment. Okay, I don't find the value here, so let's okay. Is It's here, the value, just 1 second. The most probable value, probability of total solar irradiance, a representative of solar minimum, it is this one. It's 1,300 plus minus 0.5 watt per square meter. And a previous value was this one, but not really much difference. And let's see the maps. But the maps, I think it's quite global, direct. Okay, let's see. The maps are what you may expect. Of course, more solar irradiance at the equator, and then close to the equator, and then less solar irradiance in close to the poles. And the map of solar irradiance is important also for deciphering the amount of energy that can be derived from the sun through photovoltaic conversion, for instance. And it's important because the global distribution of potential solar energy is affecting the market of renewable energy. Here you see also the legend, and you see that indeed the dark red is, the extreme value of the scale is it is expressed in kilowatt hour per square meter. So it's a different unit. So it cannot be easily compared with the value that I gave you before. Okay. Here there is a list. The most important greenhouse gas is carbon dioxide. And the problem, there are other important greenhouse gases. I would like to mention methane. It's extremely important and is also released naturally, like CO2. CO2, part of it is released naturally by ecosystems and by the oceans. Another very important greenhouse gas is water vapor in the atmosphere. It's very effective. Water vapor, however, has a time of residence into the atmosphere that is much lower than the time of residence of the CO2. And therefore, it becomes more concerning the CO2 emission rather than the emission of water vapor. Because, of course, when something is very long to be accumulated and resolved, then it becomes more concerning, because any remediation, any solution to the impact takes also a long time to be implemented. About the CO2, one important thing, the oceans are a very important sink of CO2. They can absorb CO2, and then the impact, the consequence is an increase of acidification. The ocean can also release CO2, and in particular for an increase of temperature, the oceans release a lot of CO2. And this makes the interpretation of the relationship between CO2 concentration and temperature more difficult, because you don't know if CO2 is responsible for the increase of temperature, or the increase of temperature is responsible for the increase of CO2. And I want to show you a graph which is very significant in my opinion, which I need to take from my website, and let's go to this lecture here on let me see, not this. There is a lecture on climate change and water cycle, which I find in lecture notes, and it's also linked, I was forgetting it, in our lectures, so science of climate change. Climate change and water cycle. Okay, let me look at this graph here. Okay. So this graph, look at the screen, upper panel. And first of all, thousands of years ago, in the horizontal axis, you start from 450,000 years ago, and you reach the current time. This is a reconstruction of the temperature. There are now reconstructions of past temperature for 3.5 million of years. So this is only 550,000. Okay, so it's relatively short in terms of paleoclimatic reconstructions. So first thing, you see that we had periods with higher temperature with respect to today. These were the periods where the Earth was without ice caps. First thing. Second thing, we had much colder periods, and we know that. Okay, we had during the last glaciation here until it started to recede. It was about 11,000 years ago. So during the last glaciation, we had about 8 degrees less than today. This meant a huge expansion of glaciers and a sea level that was below the current level of 120 meters. So you understand, -8 means that the glaciers got to Verona. It would be a disaster if it was today, of course. And the sea level went down of 120 meters. Again, it would be a disaster if it was today. This is the first thing. Second thing, during a period with no suspect in terms of human activity, you see that the CO2 concentration is in line, it's synchronized with temperature variations because, as I said, the ocean releases a lot of CO2 during warm periods, and therefore it's not a surprise. So the question is, again, is it the increase of temperature triggering an increase of CO2 concentration, or it's the other way around? The answer is quite complicated because in order to understand something, we should analyze the timing of the past changes. Who came first, CO2 or temperature? And there is a lot of research with controversial results ongoing on these issues. Just wanted to let you know the message. This is something, the association between average temperature in the Earth system and CO2 concentration is occurring also for natural causes and is something really complicated. Going to finish. Okay, it was not here, but was the presentation here. Okay, so just keep in mind this key message, and I think we can stop, sorry. We can stop, yes, here, because now we are talking about scenarios of CO2 emissions, another important driver next week. Thank you. If you have any question while I close by, feel free to ask.
Professor?
Yes? Yes, please.
Yeah, about the last slide, about the graph between the CO